The population growth of a colony of ants is modelled by n is equal to 1000 e to the 0.15 t, where n is the number of ants and t is the time measured in weeks. After how many weeks will the colony grow to more than 5,000 ants? Let's look at that first. So we've got that n is equal to 1000 e to the 0.15 times t. We want to find the value of t when the number of ants is 5,000, so we put 5,000 is equal to 1000 e to the 0.15 t. Dividing by 1000, we're going to get the 5 is equal to e to the 0.15 t. Taking logarithms to base e on both sides, we're going to get ln of 5 is equal to ln of e to the 0.15 of t. Now applying a few rules of logarithms, we've got log to base a of x to the r, which is what we've got here, is equal to r log base a of x. So that means I can take this power and put it down in front. So we're going to get ln of 5 is equal to 0.15 t ln of e. Now ln of e is the situation where we got log to the base a of a is equal to 1. So this bit here is equal to 1. So we end up with 0.15 t is equal to ln of 5. Therefore t is ln of 5 divided by 0.5, which we work out on our calculator. T will be equal to 10.7 weeks. So therefore, after 11 weeks, the colony will go over 5,000. What is the rate of increase in a population after 4 weeks? Now, if n is equal to 1000 e to the 0.15 t, now rate of increase is going to be, or rate of change would be dn over dt. So that means we have to differentiate this. Now to differentiate a function like this, what you do is you take the power up here and you differentiate that, so it's 0.15, and then write down the same thing again. So 1000 e to the 0.15 of t. That's going to give, when t is equal to 4, I'm going to leave it like that, but I could simplify it by doing that. But when t is equal to 4, dn dt is going to be 0.15 times 1000 e to the 0.15 times 4, which if I work out my calculator, I'm going to get 273.31. Therefore, the rate of increase after 4 weeks is going to be 273 ants per week. Show that dn dt is equal to kn, stating the value of k. Well, if we had n is equal to 1000 e to the 0.1 t, and if we, from part B, we already differentiated it and we put dn dt, and this is why I left it like this, 0.15 times 1000 e to the 0.15 t. Well, here we've now got n, and therefore dn dt is going to be 0.15 times n. Therefore the value of k is 0.15. What is the increase in the population when there are 4,000 ants? So we now put n is equal to 4,000 in this, what we've just calculated. So we're going to get the rate of change, or the rate of increase, will be 0.15 times 4,000, which will give me 600 mice per week. If it was a decrease, then the number in here would be negative. The k would actually be a negative value. Finally, is the model appropriate if m becomes large? Well, no, because the model does not take into account the amount of food and resources in order to sustain the population, or the number of ants that die. Okay, so there's been a video to show you how an exponential model could model a colony of ants. I hope you've understood, and I thank you very much for watching.